Let's get started. This is Fred Schenkelberg, and I wanted to talk about some really fundamental stuff, some basics. A couple of years ago, I did a whole series. I think I did 10 webinars in the year on fundamentals of type stuff. And I was going back over that list and looking at some of the updates I'm doing to the Ashendo site and realized there's a whole bunch of other topics that really wanted to cover in a more fundamental way. And so that's why I'm bringing back this series. And hopefully you also see the changes occurring to the Ashendo site as I start adding in. I'm not really sure of the title of it yet, but it'd be like Ultimate Guide to Safety Margins or Everything You Needed to Know About Safety Margins or some other cool title that basically says this is everything you need to know, and make it a long form post. I'm not limited by page length like in publishing a book or anything like that. And also I can link to all the content or much of the content that's available on a particular topic on the site. So kind of as a annotated bibliography, but also a standalone useful article. And one of my thoughts is that is an anchor piece of that would be these webinars. So if I do a page just on safety margins or margins of safety or safety factors, um, I could include the webinar recordings of it and so on. So hence the coming back around to some of these topics and cover them from a fundamental way. And I've also found that looking at the metrics is that these fundamental topics tend to get a lot of traffic. So when we do the live event, and I know it's people's schedules and events are going on and meetings are called and so on, but we'll get, a reasonable audience. We get some participation. I always enjoy that. And I hope you do too. Yet we get hundreds and hundreds of views of the recordings. So hopefully the content will be another piece of the evergreen on the site. So let's see if my computer will continue to operate here as I advance the slides. All right. So part of creating a product or setting up a system or a factory or facility of any kind is that we want it to be resilient to some extent, to withstand the environment and the use conditions, such that it continues to function. It continues to do what it's supposed to do for its, expected or its lifetime. And so that's one aspect of what we do in reliability engineering is work with teams to help them create a resilient product or system. Now, the other one aspect of this, and this became quite a thread on LinkedIn, an article came up about the bathtub curve by Enrico Belafonte that talked about the flat part of the curve as being, if you want to improve that, you need to make your product more robust. And you can make your product more robust and it'll help in early life failures and wear out also. So for example, if you make a brake pad a bit more robust so that it didn't wear as much per application or it had a thicker pad so it would last longer and made it out of material that handled lower and higher temperature swings and all those other aspects of it, it's more robust. It's more able, and I think I can hear my English teacher saying, use proper English. It's more better at being resilient to the stresses it sees. And that's a way to defer the damage that's being done to a product when it gets stressed closer to its limits. And as we know, not everything is like solder that's eutectic, where it gets to a specific temperature and then it melts all at once. Many things incur damage much less than their melting point. For example, they'll start breaking apart slowly or so on. And there's a continuum of damage that occurs. Well, if we make something that's a bit more resilient to the stresses, we inherently are making it more robust to those stresses. So that's one concept here. Another is back to our original goal, is the idea is that we're trying to make a reliable product. And that's kind of where I wanted to start with a common ground is that's really what we're trying to do. Yet that's not the only thing we're trying to do. It also has to be of service to the customer that they get value out of it. If it's so expensive or so cumbersome to use that they get no value out of it, well, they're not going to buy it. They're not going to use it. They're not going to recommend it to anybody. So reliability is in concert with its cost, its utility, its serviceability, all the other illities that are out there, but primarily the customer satisfaction. Are they getting value for the functionality that this product or system provides? And is it last long enough? And so making a reliable system is just, as always, a part of the trade-offs that are made in creating a new product or system. And that I think that's going over some old information, but it's worth repeating here is that we can make a very safe system, yet if nobody wants to use it, it doesn't matter, right? The safest car is the one that never gets driven, right? Eventually it'll rust and you might get a cut by some exposed edge. But the idea is that if you don't get on the highway, you can't get in a traffic accident on that highway. Well, that's not all that terribly useful. Now, I guess there are some cars that people buy and just put in a showroom someplace, but that's not really the market we're all in, I don't believe. So one of the issues with setting a margin, as you probably already know, is, well, how much do we really know? And I'm going to spend a bit of time talking about, what do we know? What do we need to know? And how well do we actually know it? And then we'll talk about some of the ways that we can go about doing that. How do we get this information? And it's a continuum like anything else. Sometimes we just guess, and sometimes we really, really need to know. And what do we do in that circumstance or that case? All right, so let's talk about stresses. These are the things that happen to our product or system when it gets out in the wild, right? And I use the smaller font. I don't want to get too small, and I probably could fill this screen 2 more times easily with just off the cuff types of stuff I've run across or I've seen or I've done. And I fully imagine that if you drop in the chat, what's your favorite stress? What's the stresses that you know the most about, or what's the stresses you know the least about? I remember way back when my days at Hewlett Packard, one of the things they had done, and it was my predecessors and a handful of engineers across the company, is they went out and measured the power coming into the different pieces of equipment. So in homes, in businesses, and in factories. And they monitored the power, the voltage and current, looking for spikes and drops and sags. And each of these things had a definition, so many milliseconds and such a percentage change from nominal and stuff like that. And they went out and measured this stuff. And they found that if you're going to create a product and put it in Japan, which I believe is 100 volts nominal current or nominal voltage on the wall outlet, it is really, really close to 100 volts almost all the time. There's very few sags or dips or spikes or anything else. Well, that's not true most everywhere else. Now, I don't know of a standard that lists what are the power quality in different systems. There's standards that says, like in the US, is the power will be 120 volts, 110 volts, plus or minus 10 volts. And that's kind of what the power companies are signing up to do. Now, if you actually go measure it, you're rarely going to see it at nominal. It's one of these old issues that if it's in spec, it's good enough. Where in Japan, as many of you already know, is that in spec is not good enough. It has to be on target. It has to be at nominal. Now, that's just a set of stresses right there. So I'm going to pause here for a second. Did I miss any? what are the stresses that you're seeing? Drop that into the chat window. And while I'm waiting for a couple folks to hit the keyboard, about the only one I've not directly dealt with is ballistic shock. I'm kind of glad of that, but I actually got just a short consultation with a team that was doing um, um, uh, uh, I want to say armor plate, but it wasn't. It was bulletproof vest is the colloquial term for it. They had some other name for it. And they were going to go off and do shooting at it, basically, with different rounds and different kinds of things. And they were more working on a sample size issue of doing that. But other than that, I've gotten to be involved with almost all of these. I think I missed one of my favorites, which was for the folks in the South or in Texas in particular, is I think they're called fire ants, which have a bite that really does hurt a lot. Creates a burning sensation. Had a product that was susceptible to those, and it was a long story, but there are a lot of stresses, right? Now, some of these we know way more information than others, and we know the effects of these better on some than others. And some we have very little or sketchy idea of information on it. Yeah, corrosive environment. I ran into it was a modeling, as a clay modeling facility for a new car design back when they used great big chunks of clay. The clay itself had a sulfur compound in it that just loved eating electronics. And there wasn't really a good way to design for sulfur exposure, but they ended up using remote computing and rather than putting the sensitive electronics in the same room. And Michael, hydrogen embrittlement, is that a failure mechanism or is that a stress? Is the hydrogen itself the stress, the hydrogen concentrate that causes the embrittlement? And if you're using materials that would be immune to that, then you could deal with that stress, for example, right? Or is that something else? But yeah, a couple of ideas there, a couple of thoughts. It's daunting when you sit down and start brainstorming, what are all the things that could cause your product to fail? You know, we do that in FMEAs, we do that in just brainstorming. We look at failure analysis. We start thinking, well, what caused this? What was the issue that led to this failure? And we often think about the stresses. Was it loaded too heavy? It was a structure that was to hold 100 foot-pounds, and somebody loaded it with 500 foot-pounds and sheared it right off. Well, the stress is the stress. It will see what it sees, and we may or may not actually have thought of it. There's plenty of stories there. Seawater, yeah. What's called along the coast? It's salt fog when the coastal low cloud cover comes in the mornings usually. It's just full of salt and it will corrode all kinds of metals and all kinds of other stuff pretty darn quickly. So good. A couple extra one. Vandalism. Yeah. I think one of the, if not the dominant one, but one of the early unforeseen environmental problems with solar panels, solar arrays, was somebody come by and shoot at them. And that would cause all kinds of havoc. Right. Now, each of those stresses we can quantify in some form or another. Some things like gunshot would be, you know, maybe a count or looking at the range of different amounts of damage they do or whatever. There's probably a way we can quantify that, even if it's just count data. But let's say it's voltage coming out of the socket, out of the wall unit. Now we can make a bunch of measurements so we can say, well, what's the average voltage we get? And it might be close to nominal over a period of time. Or we could say, well, let's measure a whole bunch of this and measure it every 2 minutes or something like that for 2 months or for the whole year. And then we get a min and max, or we get a 90th percentile or 10th percentile, or we might even get a whole distribution. And it may or may not be normally distributed. It may be bimodal. It may be seasonally, varying. It may be a time sequence type stuff. It may be, I can fully imagine that as an office building gets fully loaded with people through the day, that the stresses will change. The voltage that you're seeing will change. The temperatures will certainly change, and so on. So part of the process is, what do we really need? How well do we need to know a stress? Carl just listed a stress called lightning. Yeah. I once got asked, well, how often do we see lightning strikes where our products are being sold? I'm like, I don't know, and I was able to find some weather data that would register lightning strikes, but it was kind of cumbersome to deal with. But I did find that the Oak Ridge National Labs in, I want to say Tennessee or Kentucky, somewhere in that part of the country, actually had a facility that really studied lightning and where it was happening and why it happens and all the other good stuff and how do you protect things from it. And they had a table full of how often and what strength of lightning occurs in different regions of the country. And it was perfect. It was exactly the data I was looking for. I had no idea it existed and I started poking around looking for it. And as you can imagine, it's seasonal. When we have lots of the summer thunderstorms or hurricane season, those kinds of things, there's a way more lightning than other times of the year. But the idea is that if you're going to design something that's going to be outside on a pole, for example, and it may get struck by lightning, one of the things you're going to need to know is, well, how often and how intense, in order to understand what's the stress that you're designing for. Now, not a whole lot of people design things to withstand a direct lightning strike, yet some of our products do need to do that, or even a close strike. And there is data available on that. So it's a way to go look for it, go find it. What about fire ants? That was one of the insects in general, but this one product was a power meter that was where the power line was coming into the home or apartment was buried. And the meter itself was in a box and it was buried. And the fire ants really enjoyed the electromagnetic field generated by that device. The cable itself created a weak field around it, but the meter, for whatever reason, I don't remember the electronics on it, but it created an attractant to the fire ants. And they would eat through seals, polymers, just about everything, to get closer to that electric field. And so they were losing these power meters because once the ants ate through this stuff, then they would moisture and other debris and other things and corrosion and so on would take it out. And so the idea is, well, how would you measure that? How would you go about doing that? And one idea was just there was like a sweet spot for fire ants to, one, pay attention to an electromagnetic field and to want to get closer to it. And if they could dampen that field somehow, so it was really the intensity of the field and the species of fire ants and what's their attraction to it. And they tried all kinds of different things, but one of their standard tests on a new product or a new system, as they were trying to figure out how to protect those devices, would send it off to a lab somewhere in Austin, Texas to go do the testing. I'm glad I never got invited to that. Oh, and part of HVAC compressors. Oh, great. I'm glad I don't live where those guys are. They, they just don't sound like pleasant insects or stresses for a product. But even an insect stress or mold or fungus or driving rain or you name it, even lightning. There's a lab in Massachusetts I ran into years ago that would replicate electromagnetic pulses. So if lightning was close by or a nuclear bomb went off and created this EMP as stress, you could test your product for its resistance to it. And so they handle lightning and EMP. And it was quite an elaborate, expensive lab. Yet if you need to withstand those stresses, there was somebody out there that had a way to create it. Not that we want to create lightning in our own labs. That might be a little bit too exciting. So part of the issue is that the standard text, the places I went to look for, talking about margins, was almost always based on averages. Now, what's the issue if you only deal with the average stress and the average strength? Yeah, tornadoes don't typically be average. Tornadoes and earthquakes are tending to get bigger. Well, tornadoes are, that's for sure. But what's the problem if I only use the average stress or even just the min or max stress? What are the issues with designing a product using just that infantry? Yeah, the average is generally not stressing it. Those we get pretty good, but if it's say 2 sigma above average, it might be a higher load. I'm just going to use a load on a beam, for example. If the average load is 100, but within reason, we're going to expect to see a 200 pound load or weight on it or mass. Did we design for that? Now, most designers understand that the average is just the average, and there's some variability around it. And so part of margining is to account for that variation. Yet what I found in the text, in a handful of textbooks, was just to use the mean. And I thought, we need better information than that. So one of the things, and I think I have it in my the link here. This is for a Department of Energy paper that was defining margin of safety and safety factor. And they were using max allowable load or strength or expected stress versus the extreme or ultimate stress, and using variations of that which were out kind of in the min-max type of ranges of information. And it didn't quite define what that was. If I come up with a strong tornado, then I think they're actually talking about last year with hurricanes is coming up with another level, level 6 hurricane instead of just a 5, because they're getting bigger and bigger. But the idea is that if you use, well, what's your expected max load? Well, what if they put another pound on? What if they add a little more weight or mass to this? Then do we have the appropriate margin anymore? Or is the margin itself to take into account that variability, that uncertainty? So as we go out and measure stresses, it's really important to measure it as well as we possibly can over the entire process. Now, of course, there's things that, and this is where we have to dive into failure mechanisms. And unlike mentioning the bathtub curve in any reliability presentation, many of you know that I almost always talk about mechanisms. We need to understand, well, how does our product fail? And many times, the failure is either a sequential application of stresses, say thermal cycling that creates a crack, and then moisture, humidity, and freezing temperatures then propagate that crack, or it permits then contaminants to get within an enclosure, for example, and cause corrosion. As long as the enclosure is sound, we don't have corrosion. But that's a set of sequential damages that leads to the problem. Sometimes you, like with electromigration, we need a voltage, we need some humidity or moisture of some sort to cause a way for the ions to actually move, and the right, let's see, voltage and temperature accelerates it. If we have all three of those things, if we're at absolute zero, then we won't get electromigration, but it's pretty difficult. So we try to control the humidity or the voltage density in order to minimize that. But I only paired things here. There's some stresses that lead to failure mechanisms that are 3 or 4 or 5 things, or they're sequential. You shock it 2, 3 times, and then you get variations that lead to openings for other problems to occur. Right. So I wanted to spend a good amount of time just on the stresses. There's a whole lot out there that we know something about, and oftentimes we don't know enough about. And one of the things I want to caution you on, and I've run into it over and over in my career, is that the international standards and the local standards and even internal standards are basically a threshold, a minimum threshold. Time after time after time, somebody, and I just got this question a couple weeks ago, is what's a good standard for shipping via ground systems? What's a good standard for that, for shock and vibration? It says there isn't one. Put some instruments, put some accelerometers and a data logger into your products and ship them around to yourself and measure it. Because the measurements you will get is that actual shipping system, and it will be nowhere near what the standards call for. And then by nowhere near, I mean much, much worse. The standards are old. They are minimum standards that this old committee could agree on, and they are not going to lead you to good information. If you pass the standard, doesn't mean you're going to pass FedEx or UPS or any of the other carriers. Go measure it yourself. And it is cheap and easy to do, and you get way better data about how to do it. And that goes for almost all of these stresses, is go, start with the standards, but very quickly, if you find out that your product's susceptible to that kind of stress, go measure it, because passing the standard is a false security blanket in my regards. Now, how about the material side of this, right? Yeah, ISTA and the rest of them are all minimum standards. I haven't found any of them that are actually on target for what stresses our products are seeing. And so now let's switch over to materials briefly before we get into the actual margin calculations and so on. Now we create a product that is strong enough, hence the strength, to withstand or to tolerate or to accommodate whatever those stresses are. And so there's all kinds of different ways we measure the strength of something, and like capacitors, we often use a voltage withstand. So if I have a capacitor, electrolytic capacitor that has a 10-volt rating, well, if I apply 20 volts to it, I'll probably punch through that dielectric, and that capacitor will no longer be a capacitor. So part of the idea is with vendors and components and material properties and so on, is we get an idea of, well, how strong they're actually supposed to be. And depending on the type of stress being applied, voltage may or may not be appropriate. I know with the ceramic capacitors, it's their ability to withstand bending before cracking. Remember, they're ceramic. They're just basically pieces of glass. And one of the easiest ways to damage an electrolytic capacitor, or I'm sorry, the multi-layer ceramic capacitor, is just to bend it. And it could be from the manufacturing process. It could be from installing into a product. It could be in the vibration or shock it sees during shipping. All kinds of things that can lead to just enough 3-point bend that it breaks. I've even seen a ceramic, or not a ceramic, a crystal an electronic component called crystal that actually has a piece of crystal on these trays inside the little can. I've seen those break. With enough flex, they will break. They're glass, essentially. Yet it's a combination of, we're putting together all these different components with all kinds of different materials. And our starting point is often the data sheet. What strength is it supposed to be able to deal with? Now, we also go into finite element analysis and all kinds of modeling and all kinds of simulations work and testing to see if it actually has enough strength as expected strength. I'm thinking of the Dreamliner, I think it was them, or the 7, was it the 777 that had the first composite wings? And they built a wing and bent it to see when it would yield. And it was like 20% stronger than they expected, which meant it was heavier. But they used a lot of modeling of that material set before they went into the lab. Now, sometimes it's expedient just to go straight into the lab. But when you got a, $10 million prototype wing, you're not going to get more than one of those. But yet, if you really need to know, you spend the money to estimate or measure the strength of your product. So there's all kind. Years ago, we were concerned about voltage withstand for capacitors, and they were basically a commodity. But we found a lot of variability between different vendors, and so we would take just a small sample. We didn't do anything terribly sophisticated, but we would take a handful of capacitors, stick them on a test board, and slowly ramp up the pulses of voltage until the capacitors failed. The variability was amazing. Every now and then we would run it until we'd kill all 20 capacitors, but some would fail at 10, 15% above their rated voltage, and others went to 300% above their rated voltage. The amount of variability was amazing. And it all had to do with the amount of variability of applying the dielectric. Now, that also changed the inherent capacitance of these things. And so we tended to then prefer the vendors that had much more consistent ability to create their products. So there's a bunch of other factors at play in here. But the idea is that there's lots of ways that we measure the strength of our product or of our components and elements that we're dealing with. And again, we use averages, or we use min-max or distribution or some other way of doing this. But the idea is that if you don't measure it, you don't know. And it's really hard to do stress strength calculations or margin evaluations if you don't know how strong your system is, your product is, your components are. So if you know the stress, let's say we know that we're going to see upwards to 200, or I'm sorry, upwards to 100 pounds of mass at any one time. If we don't know if that metal beam that we're working with can withstand that load, it's really hard to say what's our margin. Now, we can do all kinds of estimates and calculations, and sometimes we go do measurements. But the idea is just like with stresses, the more we know, the better information we have, the more accurate we can estimate what is our true risk, what's our ability to withstand this stuff. And so same discussion as with stresses. Now, one of the things I've run into a handful of different engineers that just don't get it is the book strength that you get on the data sheet is one, it's not always true. It varies right out of the factory, right out of the mill, right out of the mold. The actual strength of something for whatever metric is important to you is going to vary. It's just a fact. The atoms are arranged differently and it will end up failing at a different point. That's just the way it is. Now, add time. all of these wear type things that we deal with, right? All these different ways that things can fundamentally degrade the strength of that particular item. Well, how fast does that go? How quickly does it go? What environmental factors accelerate that in the field? I once got a call. I was working with a team that was doing a satellite that was ripping around the Earth really fast, and it was going from, I don't remember the actual temperatures, but it was greater than 100 C per cycle, and it was like 18 or 20 cycles a day. And so I was like, that's actually bigger than most accelerated testing on Earth. So I don't know how to accelerate that more because we'd have to create some exotic equipment to go from minus 100 to plus 100. And I think the temperatures were actually bigger than that fast. And they ended up using margins, safety margins essentially, to give them as much strength as possible to withstand this onslaught of accelerated testing conditions that they were invoking on their system. They also did a lot to insulate the temperature swings internal to the satellite. Last I heard, it was still flying, but the idea is that strengths change. We often don't include that in these calculations. There's more times than not when I see a mechanical engineer in particular doing a CAD program that has finite element available to it. And he says, well, where's the stress points? What's the areas that we got to be aware of, and where's the concentrations, all that kind of stuff. And they know how to do that. And they whipped up this beautiful, colorful little graph and showed all these stress points, right? How does that material age? What will happen to it? And one of them was a UV exposure. It was a polymer. And I said, well, what happens if you apply the effects of that UV degradation to the model? Oh, I can do that. And a few keystrokes later, the magnitude and location of the stress concentration changed. It was much stronger, and it was in a different place than we expected. And it was because of the embrittlement of the system, the way it translated strains across that surface changed. And so it moved to where the problem would be. And if he hadn't done that, we would have designed a product to deal with its nominal characteristics. But after a few years in the sun, we probably would have failed because it was going to go after an area that wasn't beefed up to handle the effects of the degradation. So part of it is taking that into account, is when we're designing the product or the system or selecting the materials is, well, how will it change over time, and will that make a difference for us? Now, a lot of what I've been talking about is very much like stress strength calculations or derating. But at the end of the day, the more information we have about the stresses that we're going to see and the strength of our systems and products and materials, the better we're able to account for what we know. Now, the issue is that we still don't know enough, right? Hurricanes are getting bigger. I guess fire ants are getting hungrier. Whatever. There's just customers are becoming more abusive for our products, or more creative in how they use it, is a euphemism I've heard before. But the idea is that we still have unknowns. And the cost of fully characterizing all of the stresses and all the strengths is, in most cases, not something we're going to have the funding and charter to go do. So that means we have unknowns. We don't really know what's the max load. We really don't know what's the effects of degradation over time or how fast it will go. We just don't know. And just because we don't know it doesn't mean we can't design for it. I think that's the key fundamental issue of safety margins or safety factors. All right. So I went looking in a handful of different references and stuff, and the most common I found was just the mean. And I think Carl's put out a formula or two in here, a couple comments on it. But a safety factor is really just the ratio of the strength and the stress. And so if I have a item that can withstand 200 pounds and the the load that we expect to see, the expected value, the mean is 100, well, that means we have a safety factor of 2. Now, the link I put up there was from the Department of Energy, and it was aimed at the nuclear industry. And they were using allowable load and allowable stress versus the ultimate load or ultimate stress. And I they didn't define how would you determine what's the ultimate load or ultimate stress. The allowable part might be what your equipment is rated for, what it's safe to do, this pump is going to see 100 PSI across it. So that's its allowable load. And there's a little bit of design margin in that and so on. But that's what it's rated for. The safety valves will release if the pressure gets too high. That's the allowable load. But what's the stress? What's the ultimate load that we're going to get? Are there pressure spikes that hit this? Is there circumstances where that load will be way higher? And how do you design for that? How do you know what the ultimate load is? And they never got into that in that paper, at least that I saw going through it. But part of it is that it's actually a very simple calculation, and it can use the means, it could use the, say, 90th percentile. You could use the 3 sigma or 5 sigma or 6 sigma, if you like that term, expectation, if you have the data. The gist of it is that you need to come up with a common definition of this, because it doesn't do you any good for one mechanical engineer to be designing using means with a 2x factor and another designing at the ultimate loads, ultimate stresses and strengths and so on. That 2x factor will be completely different in its effect on the design itself. So come up with a common definition and formula for your product, for your design team and so on, so that it's well understood what each of these is. And then how do you get those numbers? And then which stresses and which strengths are we actually dealing with here? The ones that matter, that's kind of out of FMEAs and risk assessments and our understanding of the environment and all those other factors. But the idea is it's a pretty simple equation, right? So we have 2 options in the design, is that we can make our product stronger, right? Design it to withstand or carry 200 or 300 or 400 pounds of load versus just the nominal we expect of 100. Or limit the ability for loads to actually get to it. And we do that with our homes. We insulate it so that the temperature swings outside don't manifest inside the home as fast or as quickly. We air condition and we heat our homes to maintain a nominal temperature and range of temperatures, our target comfort zone that we like. That's artificial. And we do that in some products. We put fans in products to minimize the heat buildup, for example, as a way to limit the stress that's occurring on that product. So we can affect either side by design. We can mitigate the effects of the stresses if we can, or we can create products using materials that have the strength to withstand the stresses that we're expecting to see. But here the safety factor it's not exactly the margin, but it's a way of getting at that kind of concept, is that we're going to pad or over design and use all these other terms to say we're going to make it stronger than it needs to be, because we fully suspect that there's some variability in the load and it's not always 100, but we don't know the standard deviation or any of that stuff. So we're just going to double it and hope that's good enough. And then we'll go over to that. Hopefully it's not human weight standing on a scale that you're designing, and you only design it for its max ability to withstand 200 pounds. That might not work. in some parts of the world. All right, well, that's safety factor. It's pretty easy. Margin of safety, or safety margin, as I call it, but margin of safety is, I think, the proper term for it, is actually the safety factor minus one. And if you work out the algebra on that real quick, it's the strength minus the stress, which should be positive, doesn't have to be. You can have a negative margin of safety. It's probably not something you want to bring up and brag about. And divided by the stress. And so here, using the exact same numbers, my margin of safety is 50% or 0.5. Either works one way or the other. I think one has a little bit different interpretation than the other one, but it's the space between our strength and stress. And so it's very, very similar, not as sophisticated in mathematics and everything else as doing the integration of strength and stress overlap, for example, which is easy or trivial if you're both normal distributed, which may or may not actually occur. So it might become more of a calculus problem, but we can do that. Here it's just a ratio, right? It's the difference between the two divided by the stress. And here again, it gives us the same set of options. We can make our product stronger, or we can mitigate the stress and condition it out or mitigate it out or avoid those stresses of some sort. Now, these two formula are dirt simple. And again, like with the safety factor, we can use means, which I don't recommend. I think that's kind of pointless because it really misses the full story of, well, what's the range of these stresses and strengths that we're dealing with. And so using, say, a percentile or using the entire distribution and actually doing a bit more sophisticated math may give you much better answers than just using the averages. If you got nothing else, averages, this is a starting point. It's better than not doing this, I imagine. But again, it goes back to your local policy of how do you define these things? And for critical elements of your system, how do you go about estimating the loads and the stresses, what those values are, and what's acceptable and what's unacceptable? Because you can play a lot of games with it, obviously. So set down a clear policy of what's the formula and how it's interpreted and where's the data come from. Because if you make a few assumptions, this could be really simple and meaningless. So it's something, a margin of safety on your margin of safety policy, I guess is what I'm saying. And then finally, how do you implement this stuff, right? It adds cost to your product. It means that you have to put a bigger bracket to withstand the load, for example, on a beam, using a very simple example. Or you need heavier materials, or you need to use metal instead of polymers if you're worried about yield strength, for example. The trade-off is often not part of the design process, right? We have a target date, so we have a time to market push for, say, a consumer product, or we have a cost push for a product that's in a highly competitive environment, and we're looking at a pricing pressure that in order to have a margin, we need to be very conscious of the cost of each product that we build. And so, or it may be driven by functionality, and we're going to skin through this other cool feature because customers really want it, or we think they really want it. And those all take resources away from actually creating a product that's reliable. Or if you're in a good group, they work in concert with that. What's the trade-off? How do we get all of these other things and still make it reliable? Well, the hard part is that reliable isn't that it has a huge safety margin. It has an appropriate safety margin, right? And I use the example in at least the way I just think of this is that if you're on an aircraft, the attachment of the wing to the fuselage, especially at places of critical stress and strains that are seen in the common flights or in flying through a storm or something like that, those probably have a very high safety margin. And it's set by policy. How sure do we need to be that that part of the aircraft stays intact under all kinds of different conditions, some of which we know and some of which we can only imagine? Because the consequence of that wing falling off is pretty bad. I don't know that of too many aircraft that can fly with one wing. It'd be a really skilled pilot to make that happen. Whereas the tray in front of my seat that I can pull down and put my laptop on or a beverage on or something like that, I imagine that doesn't have much of a safety margin. It might be enough to withstand a suitcase falling on it, but probably not much more. Although I've seen them bent, and I'm quite sure they have them sitting on the tarmac ready to be replaced because and it's a weight thing, right? If they made every one of those trays out of cast iron, they'd be very strong, have a great margin. They wouldn't be all that terribly functional if you wouldn't want one of those dropping on your knees. And the weight itself would probably not pay for its functionality. We probably wouldn't have those trays if that was the only design solution for it. So the severity of losing that seat back tray is not as big as losing a wing. And so by policy, you may define what are those high severity things? What's that defined as? And those get an X safety margin. Whereas things that are inconsequential to the safety of the flight and the crew and the passengers will get a much smaller margin. And you can set that by policy. And I've run into medical device companies and aerospace companies and a few other companies that have a policy like that. And every designer knows it. And if they're working on a high consequence part of the plane or of the system, they're doing a 5X margin, for example, a safety factor. Whereas folks that are working on things that are inconsequential, if there's a safety policy in place, a design for safety type system in place, they may know that they have a 2X margin or a 1.5 margin or a 1.25 margin and a modest margin. Now, of course, this varies. If you really, really know the strengths and stresses that are applied, now you can adjust it to wherever is appropriate for cost or time to market, for safety, and so on. The part where safety margins really comes into play is when you really don't know the strengths and the stresses and all of their manifestations over time. The idea is to make the product a bit over-designed, but is it really over-designed if it works with all of the unknown sets of variability that's going to occur? I say not. I say that's appropriately designed because we still have to design for the things we don't know that are going to happen to our product. All right. It makes for a robust product, hence a reliable product. If your product is on the edge of its margins and you change vendors, and of course it's going to be the air quotes here, same form, fit, and function, and then it starts failing, well, it suggests that your margin didn't account for the variability from vendor to vendor or from batch to batch or from location in the world to another location in the world. So part of the implementation is pretty darn simple on the face of it, is create a policy and then enforce it, maybe through reviews or double checks of your critical areas of your design, simulations and testing and so on. Each organization will have to decide how they implement the policy, the better. What I have found, though, is that companies that don't have a policy at all, and I've told this story a number of times, is asking about derating, which is similar, stress strength calculations and electronic component derating is similar to adding a margin or safety margin to your product. And it may not be um, same mechanics basically that goes on with that, just slightly different application. But the idea is to build some padding in your design so that it can withstand the variability of the environment that we're in. But I was asking these three engineers, or two engineers and their manager. The first one said, "Oh, this design's easy. Our stresses are really low. I use the cheapest parts. I don't need any margin. It'll work just fine. Don't worry about it." The next person was, "This is it's very harsh environment. We got to really think about this. I gold plate everything. I get the most expensive components I can find. I make sure they're as strong as possible." And it turns out they're working on the exact same circuit board. Slightly different regions of it. One was more the digital side, one was more the electron or the power supply side of the same board. So slightly different sets of circuits, but the exact same card that was sitting in the exact same box. And one was, it's easy, no problem. The other one was, it's horrible. We got to gold plate everything. And then the manager said, "Oh, it doesn't matter. We don't measure any of this stuff anyway, so they can do whatever they want." And so now on top of the variability of the stresses, the known and the unknown stresses, and the variability of the stress of the material strengths, both known and unknown strengths that we have, and their degradation with time. Now we have two engineers with adding another layer of variability that one's like no margins, one's the highest margins they can possibly get away with and still get a functional design. That adds another whole level of complexity to a product that is just going to lead to failures. And it did. Their products were horrible. They're now safely out of business, so we don't have to worry about it. But the idea is, if you're going to implement it well. And it might be part of the director level or higher of an organization to reinforce and encourage and endorse the use of these policies. Now, if it doesn't have pushback against the cost, then the cost is going to win if that's the top priority. But where's the balance? Where's the trade-off on this? What's the appropriate calculation for how valuable is having the appropriate margin? Right? And when it's important, we'll go do the calculations. What's the chance of failure of that wing snapping off? And is that acceptable to have, as Boeing is finding out, is having one door blowout is really not a good thing for their sales and for their business and margin and their profitability and everything else. Imagine if that would have been a wing because it was missing a couple of bolts, for example. Hopefully that won't happen. Not that I'm heading to the airport anytime soon. But the idea is that for the areas of high consequence, we go to the effort to make it work. For areas of low consequence, it's still a failure. It affects customer satisfaction. It affects our ability to resell to a customer. It affects our profitability because of a product return. We can calculate that. And we can estimate the consequences, even if they're not over the top severe. And what's the probability of those things happening? We can use our own field data to get real numbers or close to real numbers of what's the cost of something not being designed with enough margin. So part of it is that the concept of safety margin is really, really simple. The devil's in the details, though, is that we don't know enough about stresses, the mixture of stresses, the combination of stresses, and their values and variability, not to say anything about the materials and the mixtures of ability of those things to perform as expected or not in all the various ways they change over time. And so the basic idea is safety margin or derating or stress strength calculations, they're all similar, but it's a way to create a product that's robust to the environment that's out there. So I'll leave you with this question is, how do you guys implement this? And if you don't mind, what industry are you in? I suspect medical and aerospace probably have a system in place that deals with this, whereas consumer products, you might not, or maybe you do. What's working for you? All right. Well, that's the fundamentals of safety margins. And there's obviously a whole lot more you could talk about. I did do a webinar on, finding and working with the weather data. I should probably link that into here because it was a great way to get all kinds of information from temperatures to humidities or moisture content, I should say, uh, rain, wind speeds, all kinds of stuff that we often will need to know if we're going to have anything that's outside. So, all right. So I'll take a look at some common other questions and comments here. Let me get caught up. Let's see. Yeah, nobody wants a boiler explosion. And I remember the factories that I don't remember if it was I think it was following the code, but I think it was county or maybe it was the state would show up every year or 2 years and they would measure, I think it was wall thickness. Um, or maybe it was something else they were measuring. I was pretty new to the organization and I was told, hey, Fred, go host this guy, show him where the boiler is. And they made a handful of measurements and put a sticker on it saying it's inspected and it's good. Um, and so yeah, you don't want a boiler explosion. That would be a bad thing, especially when it's hazardous chemicals in it and your pressure vessel will spew a bunch of bad things around the air rather than just boiling water, which is bad enough, but so on. All right. Oh, thanks, David. I'm glad to know that webinar is getting used. I was trying to just step through how do you go about doing this because it did take me a while to figure it out. And I'm sure it's changed over time, but it's a boatload of good information. It's just that you have to deal with a bunch of peculiarities about it. And every now and then they'll stick some letters in there indicating they don't know the temperature at that particular hour, but you can, a little bit of Excel wizardry will get you through it. But there's a lot of data out there and a lot of information available, and the collection of the data, especially like using a data logger, they come, you can have a battery pack that will last a week if you needed to or longer, and add a couple of sensors to it. You're off and running. You've got a whole weather station floating around inside your packaging, and put accelerometers on it. You can measure, you can get a lot of great information, say within a week or so. And it's really not that hard to do. It's much more better, is back to my English teacher, than using a standard. What's your actual environment? Go find out. So with that, I'll leave it at that. I think we just went past the allotted time. Thanks for all for attending. I think Chris is back in 2 weeks. I think he's doing something on system modeling. I don't remember, as usual. And I'll be back next month and looking forward to seeing you all or hearing you all or talking to you all once again.